All right, this is a video on basic exponential functions for Algebra 2, and we'll start with an introduction and then do a few solved examples. So a basic form of an exponential function is y equals a times b to the x. And there are certainly more complex ways we could express exponential functions, and we'll look at that down the road in terms of transforming them, shifting them, reflecting them, stretching them, compressing them. But for now, we'll just look at y equals a times b to the x. A is our y-intercept, and the reason that is because if x is 0, we get y equals a times b to the 0, and b to the 0 is equal to 1, as long as b itself is not 0, okay? And we would then just get y is equal to a, which is our y-intercept, right? If x is 0, what's y? B is our coefficient that determines if we're looking at growth or decay. And we will be working with growth if b is larger than 1, and we will be looking at decay if b is between 0 and 1. And we're going to have b not be equal to 1 and not be equal to 0 for these functions, and also not be negative. Okay, we get some kind of curious complexities if we have a negative value of b. So for now, we're going to have b either be between 0 and 1 or greater than 1. When you're graphing an exponential function, you can really use that understanding of what a and b represent. And when you're graphing any function, I want you to remember you can always just make a quick table if you need to. If you're really stuck on what that function might look like, you can always plug in a series of values for x and y, or for x, and then plug in those values into your equation to determine y. Okay, and so I'll model that right here. So here y would be 2 to the negative 3, 2 to the negative 2, 2 to the negative 1, 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. And we can actually turn those into numbers. And we get 1 over 2 cubed, which is an eighth, 1 over 2 squared, which is a quarter, a half, 2 to the 0 is equal to 1, 2 to the 1 is 2, 4, and 8. I hope you're seeing we're getting a doubling pattern, right? And that's really what that base of 2 means. The b value of 2 talks about the multiplication that's happening each time x increases by 1. Okay, and so here we are looking at a doubling pattern. So this is times 2, times 2, times 2, etc., all the way down. I hope you can also see that we have a hidden a value of 1. So this is equivalent to looking at y equals 1 times 2 to the x. And that should agree with what we're seeing right here. We have a y-intercept, which is our value of y when x is 0. We have our y-intercept of 1. So we can go ahead and plot those points on our graph. When x is 0, y is 1, and we're doubling as we go to the right. And we're halving as we go to the left. And we're going to get a function that looks roughly like this. Okay, so that's a classic exponential function, y equals 2 to the x. One thing to notice is that the x-axis in this case is called an asymptote. An asymptote is a line that your function will get infinitely close to but never actually touch. So as our curve continues to go to the left, it will never actually touch the x-axis. The distance to the x-axis will keep getting chopped in half, but it'll never actually touch it. That's an asymptote. Exponential growth and decay. We have a particular formula, and it's really not much different from our standard form for exponential functions. We have y, we have a, and then slightly differently, we have a 1 plus r instead of b. Okay, so this combined together gives us our growth rate. And then our independent variable here is t for time. Okay. We have to add on a 1 because we want to include the 100% that is kind of staying present as something grows. So if something grows by 6% a year, we want to multiply its current value by 1.06 to get its next year's value. Okay, and so that 1 allows us to mathematically keep the 100% current value in its future value. So if we have a growth of 6% per year, we're going to be looking at something like this. Y equals a times 1 plus 0.06 to the t. And so that's going to turn into y equals a times 1.06 to the t. A would be our current value, the present value, the starting value, and t would be time in years in this case because it's growing at a particular percentage rate per year. The key thing to just really remember is that 6% shows up right there as the 0.06 that's being added onto the 1. A super common mistake is to do this. Y equals a times 0.06 to the t. And that would represent something whose value is being multiplied by 0.06 on a yearly basis. And so I think you can see that its value would be dropping significantly, okay? If something is worth $100 now, next year it would be worth $100 times 0.06 or $6. Okay, so that would represent decay. So this is actually a mistake in this case. So we don't want to be doing that. Similarly, if we're looking at decay of 20% per year, that means we're losing 20% each year from its current value. And what that really means is we're multiplying its current value by 80% of what it is. Okay, so we're going to get y equals a times 1 minus 0.2 to the t, which is the same as y equals a times 0.8 to the t. Again, t would represent years and a would represent its starting value. Okay, or maybe its starting amount. It doesn't have to be value in dollars. Maybe we're talking about something that's radioactively decaying. Okay, and so the amount of a material that we have at its starting point. Key thing to remember is in, let's see here, in this case, 6% per year, we're dealing with growth and our b value is larger than 1. And conversely, when we're decaying by 20% per year, we're dealing with decay and our b value is less than 1. And so that agrees with what we were talking about up here in terms of growth versus decay. If b is greater than 1, we have growth, less than 1, we have decay. Let's do a couple quick problems. You invest $800 in a savings account earning 3.2% per year. What will your balance be in 10 years? So that is dealing with growth. So we're going to have y equals our starting value of 800 times 1 plus 0.032 to the 10. Okay, and we can just plug all those values in. We want to make sure we don't call this a 0.32, it's 0.032. Okay, we want to move that decimal point 2 spots to get a 0.032. Y equals 800 times 1.032 to the 10th. We'll just go to a calculator for that. And I get $1,096.19. Okay, you should check that on your calculator to make sure I did it correctly. We can do another sort of a problem. How many years will it take to have a balance of 1050? Okay, hope you can tell that it would be slightly less than 10 years. If in 10 years we got a balance of 1,096, we wouldn't need quite that many years to get a balance of 1050. So I'm going to plug in 1,050 for y. Again, we're starting with 800, and we have our base of 1.032, and in this case, t or x, our exponent, is unknown. We're curious about how many years it'll take. This is a problem that we don't have the skills to solve right now with a basic calculator. I'm going to show you how to do this on Desmos. Okay, we're going to type in y equals 1,050, and then we're also going to type in y equals 800 times 1.032 to the x, and we're going to look for an intersection point. I'll go over to Desmos. I can't annotate the Desmos graph, so I'll just talk you through what I'm doing, and then we'll come back here with our answer. So our initial amount is y equals 1050, and then our growth equation is y equals 800 times 1.032 to the x. Okay, and we're going to be looking at just where those functions intersect. I'll zoom out quite a bit. You can see our growth function right there. You can see it does have a y-intercept of 800. And you can see that it intersects the horizontal y equals 1050 line at x equals 8.633. So using Desmos, we can determine that x equals 8.63 years. And then a last problem that we'll do an example of decay. My Honda Civic loses 18% of its value each year. I bought it for $19,500 in 2016. What will its value be in 2025? Okay, so first we need to set up, we have to be careful what our x variable will represent. It's going to represent years, but let's have it be years since 2016. Okay, I don't want to have to be plugging in 2025 as an exponent into my equation. So we can set up an equation. Y equals 19,500 is our starting amount, and we are losing 18% each year, and the years will be represented by x. Okay. We need to think about what we will plug in for x in this case, so I'll erase away the x, and we can actually plug in 9 years in here, because 2025 minus 2016 is 9 years have passed. Okay, so what we will be entering into our calculator is 19,500 times 0.82 to the 9th, 0.82 being a value less than 1, so we'll be dealing with exponential decay. And I get an answer of $3,268.58. So definitely worth a lot less than what I purchased it for, which is why cars are typically not an investment to make money on. They're rather a tool to use because they will be losing value. All right, and that's a good place to stop.